Welcome to the Math 154 videos. Today we are going to be discussing the intermediate value theorem, and more specifically an application of the intermediate value theorem where we can find that a given equation has a root in an interval. So we're going to look first at this definition, and I'm going to read it to you and we'll see what this is saying. So suppose f is continuous on the closed interval ab. So graphically, what that's going to look like, we'll have a function and say this is a and this is b, and we have f continuous on ab. So we'll just draw f and let n be any number between f of a and f of b. So here would be f of b and here would be f of a. So this is f of a, so that value on the y-axis, and here's f of b, and we'll let n be some number between f of a and f of b. And f of a can't be equal to f of b, obviously, because then n wouldn't be a number strictly between f of a and f of b. We couldn't find one because it would just all be the same. So then there exists a number c in this interval such that f of c equals n. Well, f of c equal to n, if we just follow that back, so this right here is where a function hits the value n, and so c must be there. So basically, if we're continuous on this closed interval ab, and we pick some number in between f of a and f of b, we'll call that n, then we can just sort of trace it back and find this value c where the function actually hits that number n. So that's really all we're doing here. And so to show this equation has a root in the given interval, a root just means we want our n value to be 0. So we want some place where this function f crosses the x-axis. So then we want to find a number n that's between f of a and f of b. So we need one of f of a or f of b to be above the x-axis and one to be below, and our function to be continuous. Then we can find our n in the middle. So we'll take a look at this equation, e to the x minus 4 equals negative 4x. And we're just going to rewrite that as 0 equals negative e to the x plus 4 minus 4x. So those two are equivalent. And so since we want n equal to 0, we just want where this whole thing, we can call it f of x, is equal to 0. That'll give us a root. So first we're going to check f of x is continuous on this closed interval from a to b. So our a to b is just going to be 0 to 1, right? So the 0 here is going to be our a value, and the 1 here is going to be our b value. And f of x is continuous on this interval, and that's because negative e to the x is an exponential, so that's continuous. And 4 minus 4x is a polynomial, which is going to be continuous on the interval. So we have all parts of this function f of x are continuous on our interval 0, 1, so the function is going to be continuous there. So now we've satisfied this first part, f is continuous on the closed interval ab. Now we need to check that our number n, which is 0, is between f of a and f of b. So we'll check f of a, which our a value is 0. So f of 0 is going to be negative e to the 0, and so e to the 0 is 1, so negative e to the 0 is negative 1. And then we have a plus 4, and minus 4 times 0 is 0, so negative 1 plus 4 is 3. Okay, now let's check f of b. So f of b, which is 1, is going to be negative e to the 1, so we get negative e plus 4 minus 4 times 1, which is 4, so those cancel out and we just get negative e. Now e is approximately 2 point something, it's like 87 or 78. So basically the point is it's negative. So it's true that 0 is between these, and that's our n value. So we have n is a number between f of a and f of b. F of a does not equal f of b. So this means there exists a number c in AB such that f of c is equal to n. So by the intermediate value theorem, there is a number c where f of c equals 0, because we've satisfied all of these conditions for the intermediate value theorem, so we can draw this conclusion. So here's our second example where we're going to prove that this equation has at least one real root. So again, the same thing. One real root implies that our n value is 0. Now there's no interval in this problem, so we're going to need to find one. So we want to find an interval where 0 is between f of a and f of b. Now note first that x to the 5th minus x squared minus 4 is continuous on all real numbers. That's because it's just a polynomial, so we can plug any real number into this equation. So that's good. Now we just need to find our interval. So it's always a good idea when we're finding an interval to figure out what f of 0 is. So that's going to be 0 to the 5th minus 0. So we'll just get a negative 4 for that. So we found something that's to the left of 0, negative 4. So now we want to try and find f of a number where we're going to get a positive value, because then 0 would be between those two values. So let's just try 2. So we'll get 2 to the 5th minus 2 squared minus 4, and 2 to the 5th is 32 minus 4, so that's 32 minus 8, which is going to be 24. So we'll let our interval be the closed interval from 0 to 2, which f is continuous on. It's continuous on all real numbers. And 0 is between f of 0 and f of 2, which was negative 4 and 24. So that's true. So we have f continuous on the closed interval AB, where a is 0 and b is 2, and n equals 0 is a number between f of a and f of b. We showed that down here. And f of a does not equal f of b. Good. So we've satisfied all those premises. So then by the intermediate value theorem, there is a number c in the interval, the open interval a, b, and we have the open interval a, b just because we don't want c to be equal to f of a, or to be equal to a or b, because f of a and f of b are not our n number. They're not 0. So we don't need to consider those. So there is a number c in this open interval a to b where f of c is equal to our n value, which is 0. which means there's some number in between 0 and 2, where if we plug that number in, we're going to get 0. We're not sure what that number is. That actually doesn't matter too much. All that we know is there is 1 in that interval, and there's at least 1 in that interval. There could be more, but we've shown that at least 1 exists, and that satisfies our intermediate value theorem.